Coming back from the lunch. Okay, we're going to go straight on. It was a real pleasure to have Julia Mortera here, who's also pioneered many aspects of Bayesian networks. And she's going to be talking about, oh, she's changed the title. She called me out. So, the new title, Inference About Relationships from DNA Mixtures. I just want to say, of interest to me is that we might in some ways be related, so I'm expecting a Bayes net to work out whether we're properly related. This is not just a joke, it's true. So I'm very interested in both that and the more technical stuff.
Okay, thank you, Dave. And thank you, everybody, for having me here at this wonderful place where a lot of wonderful research is going on in forensic statistics. This is based on joint work with Peter Green and part joint work also with Therese, who's sitting at the back there, and her little baby.
Oh.
The baby didn't do any work. Okay, I'll start with an example, a motivating example for this work, which puts together DNA mixtures and methods for inference about relationships in DNA mixtures. And also give you some results on two real casework examples. So the first motivating example is the following. It comes from a real case in the Forensic Institute in the University in Rome, and we have a famous Italian singer, many of you might know him. He was working on an operetta and met a very nice young dancer and began a secret relationship. Now, she was married to somebody else, she had a son, and as an adult, the son learns that he's probably not his mother's husband's son, but the singer's son. Now, the singer was very wealthy and he died, and there was a huge inheritance. So some years after the singer's death, B, the son, well, the putative son, wants to claim a substantial inheritance. And after his mother's death, and almost 20 years after B's death, his body was exhumed and the DNA was extracted from a bone. Now, this DNA is to be used to establish if A could be the son of B. And the DNA was highly contaminated and appeared as a mixture of at least two individuals.
The DNA from the bone?
The DNA from the bone was buried because it was buried for 20 years. When it's not a criminal case, they took it out, they handled it, and so it is highly contaminated. In fact, this is...
Sorry, there is a question about taking DNA from the outside of the bone.
Yeah, I don't know all the details of that. I was given the DNA, I think collagen, okay. The DNA experts can tell you more. The son's genotype, we have the pairs of alleles for the son. We have on different markers, and this is just an excerpt of the data. The alleles in this DNA extracted from the bone, as you can see, here there are 3, here there are many more. So we know that it has to be a mixture of, well, it could be 3 or at least 2 individuals. And a very important information is given by these peak heights, which we can see a bit better on the amplification through the electropherogram. As you can see, on this marker we have many peak heights. Here we have even more. Okay, the peak height is roughly proportional to the amount of an allele before amplification. But 2 people can share an allele, so it is complicated to try and find out the genotype of the individuals from a mixture. So what I will be showing you, some of this is quite technical, is a joint model for the peak heights in the electropherogram, for the genotypes, and for calculating likelihood ratios for relationships of individuals in a DNA mixture. So we want to combine a model for peak heights for fixed genotypes, a model for genotypes, and a model for inference about relationships, all in a coherent manner. Now, the model for the DNA mixture models the peak heights, and this was a paper also with Therese and Stefan Lauritsen, that appeared in JRSS. And here we considered a DNA mixture from I individuals, and we call the peak height of an individual I at allele A is roughly proportional to that amount of DNA, we said, contributed by individual I. And we consider these independent gamma distributed with parameters that are the rho parameter is the total amount of DNA before amplification. Phi I is an important parameter, is the proportion of DNA that individual I contributes to a mixture, and this is constant across all the markers. NIA are the number of alleles of type A individual I has, and 8 is the scale parameter. Now, these individual peak heights are not observable. Well, okay, sorry, then this just quickly, we actually reparameterize some of those parameters according to mu and sigma, which is the average peak height, and the coefficient of variation for peak heights from a single heterozygous contributor. So sometimes we will be using this reparameterization. So as I was saying, the individual peak heights are not observable. What we observe, okay, for the moment we ignore artifacts that occur in the amplification, which is stutter, noise, and dropout. What we observe actually is the combination of all contributions to allele A from all contributors to the mixture. Now, using the additivity property of the gamma distribution, this again is gamma, where BA is a weighted sum of all individuals contributing to allele A, weighted by the amount of or proportion of DNA that individual contributes to a DNA mixture. The model, I won't go into the details, is then extended to take into account different artifacts like stutter and dropout, all within the same model. Okay, now, for given genotypes, given proportions each individual give to the mixture and fixed values of all the parameters, all the observed peaks can be considered independent. So the conditional likelihood function based on the peak heights, okay, on all markers and for all alleles, can be factorized, okay, factorized across markers and across alleles, where each term in this likelihood function is either the gamma distribution if the peak height is above a detection threshold, which I call C, or if the allele has dropped out, so it's not amplified because it's not above a detection threshold, it will just be a gamma CDF. Now here we have this term which takes into account the effective number of alleles after stutter. I don't know if you're familiar with stutter. Means that an allele that a person's allele, a peak at A, will actually lose a small amount to the neighboring allele, to A minus 1. Okay? And we call psi the parameter that indicates the mean strata proportion. Okay. Now, for any given hypothesis on the number of contributors to the DNA mixture, so we're conditioning on the hypothesis, the full likelihood is obtained by summing over all possible combinations of genotypes. Okay, for all the unknown contributors, this with these probabilities Pn given H associated with a given hypothesis. Now this sum is, if you think about it, is astronomical in size because we have to take into account the whole repertoire of alleles for all unknown contributors. And the way we manage to resolve this is by calculating it efficiently using an appropriate Bayesian network technique. Now the likelihood function involves certain number of parameters. These could be completely or partially known. Where we adopt the method of finding estimates of these parameters by taking the maximum likelihood estimate for all the unknown parameters. Now, some of the computational aspects. As I said before, one of the problems is that sum is enormous over all possible genotypes of all unknown contributors on all markers. So the trick is to use a Markov genotype representation and to compute, to introduce auxiliary nodes in the Bayesian network to be able to compute different things. The benefits of this is, well, first of all, in the Markov representation of a genotype allows us to compute things very efficiently. The introduction of these auxiliary nodes allows us to do an exact evaluation of that complicated likelihood function simply by probability propagation in a Bayesian network. And also, we can introduce other auxiliary likelihood nodes to represent the family relationships, because we're interested in family relationships to people within a mixture, unknown people within a mixture. Now, these models have no approximations are introduced apart from some numerical maximization and differentiations that are needed to compute the maximum likelihood estimates. And the model for DNA mixtures can handle up to 6 unknown contributors. Now, the genotype representation is one of the key representations in order to solve complex DNA mixtures. Just think of representing a genotype by considering the 2 alleles in the genotype as being allocated sequentially. And we call SIA the partial sums of the allele counts. So just look here, we have this would be the ordered alleles in an individual's genotype. So these would take values 0, 1, or 2 if he has allele 1, 2, 3, and 4. Okay. At allele A plus 1, these depend on the previous alleles only through the partial sums. So we can then represent this in this Markov structure. Okay, the cues that I have here are the allele frequencies which we consider known in a certain reference database. Okay, so the genotype is modeled by a Markov structure, and computations can now be done linearly in the number of alleles. Okay, it looks strange, but this is the way we can get about having at least up to 6, even 8, I think, unknown contributors in a mixture. Now, back to our original problem. So, a lot about DNA mixtures. I am now just introducing the fact that we want to understand if there's a relationship with somebody in a DNA mixture. And examples are the motivating case. We want to know if A is the son of a contributor to the DNA mixture. A's mother's DNA might or might not be available, or is the contributor to the mixture, turning it the other way around, is he the son of individual A? And other type of relationship inference. Now, the evidence will be the DNA mixture with its peak heights and alleles, and the genotypes of those individuals that are measured. So, a general setup in order to be able to implement this into that DNA mixture model is we consider, let UI be a specified contributor to the mixture and call UGT his genotype. When what we are interested in is assessing a potential relationship between this unknown and one or more other individuals who have a known relationship to each other. Okay, and I call R the genotype of these measured individuals. So one hypothesis would be that U has the specified relationship with individuals whose genotypes are in R, where the alternative would be that U is unrelated with individuals in R. And okay, this is a DAG, as Phil was talking about. So it's mainly a pictorial representation. And in light blue are the nodes that represent that gamma model that we saw before. Okay, these are the parameters of that model. Z are the peak heights, observable peak heights. N instead are the combination of all the genotypes of the individuals that might be in the mixture, knowns and unknowns. UGT is the individual that we are interested in. This will be the distribution of his genotype, okay, of an unknown person. The yellow nodes represent the putative relationship between a mixture contributor, UGT, and these relatives who have known genotype that are in R under a certain hypothesis H. For example, our case, the first case is a paternity relationship. H would be, is UGT one of the genotype of an unknown contributor to the mixture, the father of the son who's claiming the inheritance. Okay, and as you can see from this and how Phil explained, R is independent, is conditionally independent of the peak heights once given the unknown person's genotype. So examples are measured individuals of the child's genotype, or could be the child and the mother's genotype. And we're interested in testing if U is the father of the child. Now, first let's look at the likelihood ratio conditional on UGT. So if we knew UGT, the likelihood ratio would simply be the probability of the relationship under the hypothesis that, say, he is the father of the child, given UGT, and that he is not the father of the child. In that case, UGT is totally independent, and we have, okay, this likelihood ratio conditional on UGT. Whereas the overall likelihood ratio, which is what we're interested in if U has the specified relationship with individuals in R against the contrary hypothesis, well, this can be broken down, extending the conversation to all the distribution of unknown genotypes. And one can show that this is formed by a sum of the previous likelihood ratio, the likelihood UGT specific, I'll call it likelihood ratio, conditional on the unknown genotype, times the distribution of that unknown person's genotype given the peak heights in the mixture. And one thing to notice is that this likelihood ratio will always be smaller than the maximum of this term. So inference based on the likelihood ratio in a mixture of a relationship is always smaller than if we were able to observe this unknown individual's genotype, okay, and if it wasn't in the mixture. Now, methods that we have implemented for inference about relationships, till when do I have to go, Dave?
Official finish at 2:15, but maybe if you can, to about 5 past,
Okay.
so we have time for questions.
Okay, this is the likelihood ratio that we wish. The first thing that came to mind, which we called the weighted likelihood ratio, is taken the DNA mixture program, a beautiful program written by Therese, and deconvolve that in order to obtain a set of possible genotypes together with their probability ranking, and use those to approximate this term, and then this is just easily calculated algebraically. We then moved on to thinking of a slightly different way, adding a likelihood node, introducing an auxiliary variable in our network, and maintaining that Markov genotype Bayesian network. okay, and adding a single likelihood node, and I'll show you that in a minute. The important thing is that, okay, if only the child is genotyped, we only have information on the child, or the potential child, the UGT specific likelihood ratio would be just the probability of that child's genotype if we knew the unknown person's genotype under the paternity hypothesis. Okay, and one thing to notice here is that these just depend on the child's A allele or A and B allele. Okay, so the only allele counts for the unknown contributor that are needed as parents for defining a conditional probability table for a likelihood node are those in A and or B in the child. Okay, Q again is just the known allele frequencies. So similarly, for if we have both mother and child, again, okay, one can work out the algebra, and the only allele counts needed again are those either A and or B in the child. What does this mean? Okay, this is the Bayesian network. This is that Markov representation. In the blue is the Markov representation for the first contributor to the mixture. In the green, for the second contributor to the mixture. These auxiliary variables are where we introduce the likelihood function from the gammas and the gamma CDFs, okay, and are able then to compute by probability propagation. We introduce an extra node, this child likelihood node. For in this case, I've considered just a homozygous child. It only needs to be linked to the one allele count of the one unknown contributor to the mixture. After the first approach, this was the second way we thought of resolving this problem, is introducing a meiosis Bayesian network. As you can see, it's much more complex. Again, blue, green, and these nodes are from the DNA mixtures. What we do, we capture meiosis by introducing a segregation indicator, these G nodes. And then we have the child's paternal, the child's maternal genes, and the child's alleles. Again, trying to maintain that Markov structure. Okay. Another idea was instead replacing the default distribution for the unknown's genotype. Okay, the default is based on Hardy-Weinberg equilibrium and assumed known population allele frequencies, with tables for the conditional distribution of UGT given the genotypes of the people whose genotypes are measured and which we want to test if they are related to UGT. Okay, and again, we can slightly modify the Markov structure by simple tweaks here. Again, that will only depend on the sum of the allele counts, okay, and on the allele frequencies in a database. Okay, I think it's more interesting to look now at some of the results. In the disputed paternity case, first of all, we also implemented an additional information in the DNA mixture program. We condition on information. We know that the person whose body was exhumed is a male. Okay, the singer was a male, so we condition also on that information by introducing in the amelogenin marker that information. Now, first thing, looking at the top ranking genotype. So looking at DNA mixtures, we deconvolve that. We see what the top ranking genotype is, and it's the probability of that top rank. As you can see in red, I've indicated that the predicted genotype for the top rank genotype is compatible with the child on all markers. With and without maleness, it doesn't make a whole lot of difference in this case. It might in other cases. Now, if I took, one of this probability will tell us how much we can trust it. Here we cannot trust this top-ranked genotype so much. It has a very low probability. But if we look at the whole ranking of that deconvolution, up to the third rank, they're all compatible with the Sun. The Sun was 3032 on that marker. From then on, they're incompatible, but that will lead to that sum for the likelihood ratio will just give us a zero term. Okay, so looking at the marker-wise likelihood ratios, the likelihood ratio for the top ranked, if we just look at the top rank and then consider that to be the unknown contributor's genotype, and calculate the likelihood ratios marker by marker, we can do that because they're now independent across markers because we condition on the MLEs that we find for all the parameters. The exact methods, ALN, the three methods that I showed you, lead to slightly less, call that incriminating for paternity, and they give exact answers, whereas the method based on the whole full deconvolution with all the probability weights is a good approximation because, but it is a slight approximation, so we prefer these other methods. So the top rank gives us, on the logs 10 scale, 5.67. It's reduced by a factor of about 1.75 when we use the exact methods based on the mixture. And for any prior, even of paternity greater than 1%, the posterior is bigger than 9994. So the conclusion is he is the son of the famous singer. The likelihood ratio for paternity, we then had, well, basically we made up a potential mother. With and without the mother, you can see that information, if we also have the genotype of the mother, is extremely higher. The information on the likelihood ratio increases by a factor of 550. This is again on the log 10 scale. Okay. Computational times of these different methods. The quickest is that adding the likelihood node, and then the replacing the probability tables. The one based on the meiosis is about double the time, but the one based on the deconvolution is very much slower. Have I got time for this other case? Is an Italian criminal case that you might be. Well, it was a terrible murder of a little girl in Italy. And we have three, here we were looking at three traces. They are mixtures, T1, T2, T3. We also have the genotype of the victim. And later we had the genotype of the alleged mother of one of the contributors to the mixture. We assume that there are at most three contributors to this mixture, the victim and two unknowns. And we'll see later on that the second unknown is included to account for possibilities of drop-in, which means that just on some alleles we have an allele that is not to do with the case that drops into the mixture. An interesting thing is if we look at the maximum likelihood estimates of our different parameters, especially on the proportions of DNA that we estimate for the victim and the first unknown. In the first trace, the unknown has about 70% compared to 20% of the DNA contributed to the mixture. The second, they're almost equal in the second trace. In the third, the victim contributes more than the than the unknown contributor, who we assume is the murderer. And whereas this unknown contributor contributes almost a negligible amount. Now, in this case, what we want to compare is, we want to try and identify who this unknown murderer is and see if he is actually the child of the mother whose genotype we have, or if none of the contributors are related to this person. Using these exact methods that we saw, the likelihood ratio in favor of the prosecution hypothesis that this U1 is the the child of MGT is 10 to the power 4.26, so extremely incriminating. And he in fact is in prison. The problem was that they were trying to identify who the murderer was, and they had typed villages near where that happened until they found a mother who, the person that looked highly likely to be the mother of somebody in the mixture. Now, I think an interesting thing is if we had analyzed the traces separately, all this that I showed you, we actually, the model that we have can analyze all traces in combination. And that was the result we got, that 10 to the 4.26. If we examine each trace separately, you see the first trace actually has a likelihood ratio which is reduced only by a factor of 1.05. The second trace instead and the third trace have a likelihood ratio that's reduced to about 174, 76 times that based on all traces. And I think as a Bayesian, we like to condition on all our information, so combine all the traces together and not just examine them separately. There's a problem. If we leave the contributor unspecified, now here we were interested in the major contributor because we assumed that he was the murderer. But in that problem we had a second contributor, all right, he didn't, but in any problem we could have many contributors to the mixture. These are numbered in decreasing order of the amount of DNA they give, and so we would get a likelihood ratio for the first contributor, the unknown contributor for the second and the third. How can we combine that? Well, a Bayesian way would be taking this weighted likelihood ratio for each of the contributors, but where we would have to though specify relative priors. Now, specifying the relative priors can be difficult, and I just thought about this, but I think the lawyers here will be able to say what's better. In a criminal trial, I suppose you want to err on the side of caution, so you want to report the minimum likelihood ratio. In a civil court, we could possibly take a range of likelihood ratios over a possible range of priors. Like in our problem, it was so not incriminating, the paternity issue was so strong that even with a prior of 0.01 gave us a probability of paternity of 9993. The calculations here are all done in R using a suite of functions that's freely available. This also though needs to call our Huygen, which relies on Huygen, which is not freely available package, but this in order to augment the capabilities of the DNA mixture package, a beautiful package that was written by Therese. And there we are, final remarks. One thing about these methods, they can be readily extended to different scenarios. Okay, they're not limited to the particular details of a genotyping kit, nor to the allele frequencies, nor to the number of contributors, nor to the hypotheses. Which method is better suited will depend on the complexity of the relationships. In our case, it's a paternity case. adding the likelihood node, which is, we think, one of the fastest and most efficient methods. If it's homozygous, it's linked to just one allele count. If it's heterozygous, it will be linked to 2 allele counts. So it doesn't add a lot of complexity. But in more complex relationship, there would have to be more links, and it might be more complicated, and it might be slower. And I don't know, but this idea that this work could be also useful in identifying disaster victims, where you have actually a mixture and you're interested in, you have DNA from relatives of the people and you'd like to test whether you've identified a person. Thank you very much.
This is what plenty of time for questions. Okay.
Thank you very much, Julia. The choice of the gamma, how much difference does that make using a gamma? I mean, is it done because the normal will be unidentifiable, or?
I didn't just quite hear the last part.
You've chosen a gamma distribution for your numbers.
For the peak heights.
For the peak heights, yeah. Is that picking up a degree of skewness, or is it merely a convenience? Is there a reason?
No, there's a reason. Reason that the amplification process can be considered a branching process, and that converges to gamma. That's one. Second reason, in our model, the expectation is proportional. The variance is proportional to the expectation, and we found that in many cases of known DNA mixtures. Let me think. Other reason, well, there's that beautiful property of the summation property, that the gamma is still a gamma. But I suppose, yeah, you could use other types of...
Positive.
It's positive, bravo. Yeah, Therese.
Yeah, I'll just add to it. So, for the purpose of computations, all that Julia said, I mean, you could easily use any other distribution, and the gamma is not important.
Okay.
So no properties of the gamma distributions are used to simplify the calculations.
Yeah.
So you could basically do the same with, say, if you use the Balding's model or the star mix model.
I just want to go back. Whoops, here. Right, in these nodes where you'd be, these auxiliary nodes, Boolean nodes, where you would consider with the gamma, you would put another distribution.
Could you go back to the when you did the likelihood, when you had this truncation at C, the what should we call it? The detection limit.
Oh, where was that?
It was at the beginning, fairly early.
Yeah.
What I was thinking of, if you have this, if you can't detect, should this be a truncated gamma or something? Because you obviously know it's less than C.
Yeah. Look. Depends on C. Yeah.
Yeah.
Okay.
Yeah. I'm just saying that. So I'm saying, you have to use a kind of truncated gamma in your.
No. A CDF. And up to C.
Yeah. So that would be a truncated. We call it truncated.
Yeah, call it.
Just a quick addition. We're not truncating here, Joe. We're censoring.
Censoring, yes.
Yeah, it's censoring. I don't know what it calls truncation censoring, but I imagine that was
same
meant.
Same ideas.
Yeah.
Same idea.
We don't have any censoring in this room.
Very interesting presentation, really brilliant. I really liked it. But there's one question or maybe a suggestion. So, your starting point, your evidence is a pig table list. When you say I found a pig at this allele and I had my pig heights, but your real evidence is not a pig table. Your real evidence is a signal from your electropherogram.
Yes.
Have you thought about using these signal as your evidence? Because there might be pigs that are below these. It links with your question. Might be pigs that are below these
we can actually set the detection threshold to like 0.001.
No, my question is more provocative. So
Yeah.
instead of using the threshold and saying, okay, everything that is below the threshold, I don't consider as a peak. Use the raw data from your instrument.
Yes, except there'll be a lot of noise there, and you don't want too much noise.
But if there is a bump,
But
still that's evident, right?
well, no, there's people sort of this detection threshold. We can actually set it really, really low, but then sometimes you'll be picking up also all the noise that.
Yeah, but the
So
question is that if you have a detection threshold, you are making some algorithm for detecting peaks, right? And you are rejecting peaks that are below this threshold.
No, they're not being rejected.
They're not being rejected. I'm accounting for that. I'm saying that there might be something below the threshold. These machines, sometimes they actually set, so when you get the data, it's already set at a threshold. And I'm saying there might be something. It's not that I'm throwing it away.
You're just using the information that the peak height is less than or equal to capital C.
My question is, you could use the raw data and go even deeper.
You can do that.
But I think
I
it's saying that
think-
if you have the threshold too low, you essentially have 1,000 peaks.
Yeah, you have a mess. In some cases, you'd have just
Because you have a
absolute
big
mess.
detection algorithm inside. So
Yeah, and we can set it pretty low. I mean, so that I think it might even work when, when in this low copy number DNA.
Sorry, yes, if you are not ignoring, sorry, I beg your pardon.
That's okay.
Were you pointing at somebody
I was
else?
pointing on something else, but I don't mind
Carry on.
private interchangeable order. Okay.
It felt like you were pointing at me, but I'm sorry.
Okay, we'll go with the guy behind
yeah,
the menu.
you have the table with D21, and you listed who were sort of compatible with the sun, the genotypes, and then you said that you had 30 there somewhere because you had that genotype, and then you said that here.
Yeah.
So number 4, couldn't that be if you have mutation or is
Yeah, sorry, I forgot to say,
Okay.
in this is the first step, we
Yeah,
are
yeah.
not considering mutation.
Okay.
Yeah, we have not considered. That would complicate matters quite a lot, especially in the adding the likelihood node for the child, because you'd have to have, depends on what model, maybe if you just have a one step, then you need it to the two neighboring.
reminding us?
Yeah, look, I'll show you here.
Stuttering, but on the
Here, if you account for mutation, say that could 2 could go to 1 or 3, then yeah, you'd have to add extra links. If you just consider a one-step mutation model, if you consider that it can go to any, then it can get a mess. So for the moment, we haven't done that, but you can do that.
Thank you. Thinking about my question, I no longer have a question.
Oh, okay. Was it the same one as Bill?
This is similar to the previous question. I wondered if you thought about modeling degradation of the DNA from the contributors, particularly when you're dealing with aged samples and contaminated samples. It seems like some of the DNA of some of the contributors might be degraded, and the degree of degradation might vary across the contributors, all of which could add a great deal of variation to the peak heights. Is that something you thought about trying to model, or is that?
Well, in a certain sense, for example, when in the case where we have that second contributor, right? He only is giving a very small amount of DNA, so that in that sense it would be a degradation. But I don't know if you're thinking of along the lane. Are you thinking of degradation along the lane? We need to implement that, and that's something Therese is thinking about in the DNA mixture process. That means along the lane, things
The
get
degradation
degraded.
would have a larger
Yeah.
effect on the.
We need
on
to
the
introduce
larger
an
DNA
extra
fragment.
parameter.
Yeah, so it might actually help your precision.
Good time for a final quick question.
I was wondering for this last case, you said something like the mother
was found by searching a lot of people in the villages. So I'm thinking you might have a large likelihood ratio, but there might be a very small prior probability for this person to be related. So did somebody think about this prior, or did somebody say something about it?
I haven't quite understood what you mean.
Well, if you find this person who you compared in the end.
Well, I first of all
Mother.
don't have the murderer. So I'm trying to look for the murderer. I'm trying to look for people that might be related to somebody in this mixture.
Yes, so you find this person through a search.
You find this mother through search, yes. It's a bit more complicated than that, but still,
I'm
yes.
concerned about the prior probability that this mother is actually related to this donor.
Yeah.
So it might be very small.
Might you be dealing with a region where there is a lot of inbreeding among the people?
Well, okay, well, all these complications are now taken into account, but
You don't care because you only compute the likelihood ratio, not the
Yeah.
criteria.
yeah,
But somebody
But
should
you could
think
inform
about
the
the
court
prior,
that
right?
they
you could,
did prior.
yeah, I mean, this mother, I mean, with the likelihood ratio, I'm not putting a pry on the mother.
I know, but somebody should think about the prior, right? So
Well, no, because
anybody
I'll
think
tell you the
about
whole
this?
story. In the end, they actually then took the son, took his DNA, and that's the way they found the murderer, through the mother. Okay.
Thank you very much, Studi.